Hello, Math 8 students. This is Unit 1, Lesson 12, Congruent Polygons. We're going to continue our discussion on congruence and really solidify what congruence truly means. To get us started, we have this warm-up, translated images. It says, all of these triangles are congruent. Sometimes we can take one figure to another with a translation. Shade the triangles that are images of triangle ABC under a translation. Online learners, pause the video to give yourself enough time to get this done. In-person learners, we're going to continue. I need 3 or 4 volunteers to go up and shade triangles. We'll start with Lucas, Zeta, Xander, Garrett, and if we need more, then we'll go from there. Go up and shade the ones. There's 2 pens, so we can have 2 up there at a time. Garrett took the first one. Xander, no need to wait for him. There's 2 pens. They both work at the same time. Xander's got the second one. Zeta's squeezing in to start shading the third one. And Lucas, do you want to go up there and shade the fourth one? The fourth one's the first one? Yeah. So are there any others that should be shaded? Holy cow. This is the first class who didn't shade any wrong ones. Every class we had at least one wrong one shaded, so then we had to have more volunteers go up and erase the incorrect ones. So how did you know which ones were translated? How come we didn't shade some of these other ones? Cole. What did you do with the tracing paper to help you identify that though? So you traced the original one? Yeah, we have to move it without turning it, exactly. Zeta. Good. Good. I love how we had 2 different methods here. Cole used his tracing paper, traced it, and then moved his tracing paper without twisting it. And that's how he knew exactly which ones they should be. Zeta didn't use tracing paper. She just looked at it and said, hey, ABC is going this direction. So if I see something going a different direction like this one, I know that that's a flip. So that's not going to be it. This one maybe was a spin, so we know that that's not going to be it. And so we can kind of process of elimination, figure out which ones shouldn't be there, and then shade the correct ones. Well done. Again, like I said, we're going to continue our discussion on congruence. And so yesterday, we talked about what congruence actually means. So before we move on to the official lesson for today, I want you to return to lesson 11 and reread the summary. It's also up on the board, but I want you to take a second and reread that summary, focusing on the parts that we underlined, highlighted, any extra words that we wrote down. Focusing on what does it mean to be congruent? What does it mean to be congruent? Pause the video, online learners, to give yourself enough time to review this. We'll come back together soon. All right, you've had a chance to review. You had a chance to discuss at your tables now, share with the class and the online learners. What does it mean to be congruent? Focusing on those highlighted and underlined words. Good. Tyson? Exactly. Well, that's what we wrote down here in our glossary terms where it says congruent. We wrote down that that's a rigid transformation, right? We have to be able to take one figure to the next through a rigid transformation. And that's exactly what we underlined here. And that's the key thing that you guys need to remember. So we're going to add to this from yesterday's notes. What I'm going to add here is this. This is the definition. Okay, so the definition isn't the same. The definition is that concept of rigid transformations, that I can go from one to the other through rigid transformations. A result or a characteristic is that sameness, or we can see that it says, notice that all corresponding angles and side lengths are equal. This is a characteristic. So I want to make sure that we understand the difference. Characteristic. Yeah. Definition, this is a unique and really awesome characteristic, but it's not what defines it. So we're going to focus today's lesson. It's actually very similar to yesterday. We're going to focus on using that definition to show that figures are congruent. Okay, we want to focus on that rigid transformation aspect. Now we're ready to move on to the second activity from our lesson. And what you're going to be doing is with your groups, you are going to be discussing, are these figures congruent? If they are, make sure you're able to explain how you know. If they're not, make sure you're able to justify. So these first, I think it's 4 problems, 1, 2, 3, 4. These ones you are doing with your group, with everybody actively engaged and participating. So online learners, while these students are working in their groups, online learners are going to pause the video and do these on their own. Pause the video now. Landis, what's your question? He asked, does it always have to be a translation or can it be something different? And we're going to review, it says, a sequence of rigid transformations. That would be rotations, reflections, and translations. And it doesn't even have to be just one. It can be a translation and then a rotation. It can be a reflection and then a rotation and then a translation. It could be a whole bunch all strung up together. Okay, great question. With that in mind, let's continue on. Again, we are trying to figure out, are they congruent? Using this idea, can we define rigid transformations? Carry on. All right, we're returning after about 4 to 5 minutes of working on these problems, ready to discuss whether or not they are congruent. The first one, are these figures congruent? Tyson. Okay. Yes, but also no. I like that you use the word flip. When we use the word flip, what is the mathematical word that goes with flip? Reflection, yeah. So we know that there's going to be a reflection involved. And I like how you said we're going to flip it upside down. So that's the first thing I'm going to do. Even if you have a different answer, we'll write both answers down. But I really like looking at this because most students don't see it this way. So we can flip it upside down, right? And is it exactly where it needs to be still? No, so we got to keep on moving it, right? But let's at least write down that one. And even if you wrote something else, will you add to your notes? Because I think it's great to see it in multiple ways. Yes. We're going to start by reflecting. And I reflected this one, EFGH, over the x-axis. And is it lined up yet? No. What else would I need to do? Nadia? What else would I need to do? So now we're in this figure right here. How do I continue to rigid transformation it to get it into position here? I do need to move it over, yes. And I'm not going to move it over yet. I want to wait to move it over, and you'll see why in just a second. If Tyson wanted to flip it and reflect it up, now how else can I get it all the way over here? Callista? Yeah, now I can reflect it across the y-axis. So now I'm going to reflect it over the y-axis. Just remember, this is not the geometry software, so I can flip it, but then I have to move it into position where it should be. And it should have been right here. And it's closer, but is it in position yet? No. So what is the final thing I need to do to get it into that position? Now we would want to move it over, right? So now we will translate 1 unit left. Could we have done those in a different order? Yes. But that was the order that was presented, so that's the way that I went with it. Here is a different way. Who thought of it not with reflections, but with a different way? Good. Garrett, what did you see? Okay. Hold on, what do you mean translation over the y-axis? Let's back up. Did you start with A, B, C, D, or did you start with E, F, G, H? Okay, so I'm going to move it over to the y-axis like this. Do we need to have a little bit better, more precise vocabulary? What do we mean? Okay. Help him out, Landis. Good. I like that math terminology, a rotation first. So that means I'm going to be spinning it. Now, remember when we're talking about rotations, I need to know the degree, the direction, and the center of rotation. So let's add some of those details. This is the problem that's going to take the longest. Rotation, how much? How much am I rotating it? 90, it's more than 90. Yep. Take a look right here. Do you see how this part is all up on the top? Where is all that part now? Down. So how does it go all the way to 180? Yep, 180. Rotation 180 degrees. Clockwise or counterclockwise? Fun fact, it doesn't matter. I'm going to put clockwise just to remember that we do need to include direction most of the time. About what point? Am I going to rotate around D? Am I going to rotate around the origin? What did you pick, Zeta? Yeah, good. So you found the exact center of rotation where you didn't even need to translate it again after, right? Yes, so that rotation point would be there. I'm going to pretend like we don't know that, and let's also add a translation too. But that is fantastic that you observed that. Let's make it the origin. Around origin. And again, remember, not geometry software, so while I do this rotation... Ooh, hold on. I need to pause. Rotate... I'm starting with ABCD for this one, so I need to include those directions. ABCD has a rotation 180 degrees clockwise around the origin. So it's going to look like this. That's the 180 degrees. Around the origin means that figure is going to show up right here. And it's not quite where it needs to be, so now we need to go, Callista, translate left 1 unit. But I also really like what Zeta said, or you could just pick a different rotation point and just rotate it right into where it needs to go to begin with. And we didn't have to worry about the translation. Okay, those are 2 options. We have definitely proved in a couple ways that yes, those are congruent. Let's move on to step 2. Are these congruent? How do you know? I think it's obvious, right? Okay, but I want to kind of play devil's advocate a little bit. Do you guys see a 90-degree angle here? Do you see a 90-degree angle here? Do you see this side length that's like 1 diagonal and 1 diagonal? So are there some pieces that are congruent? Yeah, but are the figures congruent? No. This one we don't need to take a ton of time explaining. I just want to say no, although they're both pentagons, because they both are 5-sided figures. They are obviously very differently shaped. Okay, number 3. Are they congruent? No, it's actually 3. Do you see how the numbers are all at the very bottom? Yeah, I kept calling it 2 in my last class too, and they had to keep correcting me. This one is actually 3. Landis, what do you think? Oh, I called on you last time. I want to hear someone else. We say yes. Someone give me a good justification. Lucas? Okay, good. I love the use of the tools. Listen to this, guys. This is a great way to identify all of these things. So we started by tracing on the tracing paper. Great. What next? Okay, but how did you move it? Let's be detailed. How did we move it? What did you do with your hands and with your tracing paper that just there? Nadia? Okay. Okay, FED. So I'll get that one into position here. So you started here. Okay. Okay, good. So that's a great use of our tracing paper. I need students to get their heads off of desks. Your ears and eyes need to be open and listening and focused, okay? When you trace it onto your tracing paper, pay attention with what you do with that tracing paper. You say you just moved it, right? But Nadia was really specific and she said, I moved it this way. And she showed me with her hands and she said that that's a rotation. When you spin it, that's a rotation. So she spun her tracing paper and maybe it spun and it landed right here, but then we have to continue to move it into place. That would be a translation. So I'm going to write that down. Yes, we rotated. The degree is a little bit trickier, but we rotated 90 degrees clockwise. Oh, I'm going to pause for one more second. Yes, rotate DEF, because that's the one that she started with. Rotate DEF 90 degrees clockwise. And again, there's lots of points we could have rotated it around. Maybe you rotated around the origin. That particular example, I rotated around point D. When I rotated around point D, it got us into this position, which we're not there yet. We now need to go 1, 2, 3 to the right, and 2 down. Are there other ways this could have happened? Yes. The key thing to understand here is, can we get to at least some rigid transformations to get us there? And as long as the answer is yes, then it is indeed congruent. Last one, number 4. Is it congruent? Cole. Good. Cole said no, because A, B, C, D, E, F, G, H, this polygon, is bigger than I, J, K, L, M, N, O, P. How can we prove that? Again, our tracing paper can be a tool. Our index card would also work too. Do you see how I've got this line segment here? Does it match up? No. What about this one? No. Are the angles the same? Yeah, the angles are the same, but the line segments are not. So, line segments are different lengths. And since they're different lengths, is a rigid transformation going to work? A transformation where lengths are supposed to stay the same? Obviously not, right? Okay, here's what we're going to do for this next exercise. In class, students are going to work with their table partners, and you're going to be... Uh-oh. I got these out of order. Hang on just one second. Let me fix that. Okay, in class learners, you're going to take turns with your partner, where one person will describe one, and the other person listens, and then you switch. Okay, so this is how it's going to work. This is not on your paper. Stop looking for it. It's not on your paper. This is the one that I'm using as an example. You guys are going to be doing the same thing for these ones on your paper. Do you find these ones on your paper now? Okay, so that's where you're going to be doing it. This is just an example. I am going to construct a viable argument. That's math practice 3. You guys are going to listen to critique my reasoning to see how I do. Okay? And what I'm going to say is this. I'm going to take A, B, C, D, E, F, and I'm going to rotate it 90 degrees clockwise. And let's say around point F. And then I'm going to translate it 1, 2, 3, 4 units to the right. Is that going to work? Who says yes? Who says no? Why? Why no? Garrett, why no? I'll repeat it so that you guys can listen again. Construct a viable argument for or against me, okay? Critique my own reasoning. I'm going to take this figure, A, B, C, D, E, F. I'm going to rotate it 90 degrees clockwise around point F. And then I'm going to shift it over 4 units to the right. What do you think, Xander? Yeah, it wouldn't land on it if I'm going clockwise, right? That shows that you guys were listening. You had your own idea in your head so you could compare it to mine. What should I do instead? I should rotate it 90 degrees counterclockwise around point F, and that will end up here. And then what would I need to do? 1, 2, 3, 4 to the right. Okay? I'm not going to take the time to write that down in the notes, because I want you guys to have enough time to do this. So again, you're working with your table partner. You're each taking a turn. One student will do this one. Then you switch. Switch again. And so on. This should take us about 5 minutes. So students at home, you guys are just going to have to do this one on your own. Pause the video for about 5 minutes to get it done. we're going to go through this next section quickly. Part 1, is A congruent to B? Who says yes, raise your hand. Who says no, raise your hand. Okay, why no? Okay, that is interesting. You might have had an error with your tracing. Like you said, it might have been your drawing, because this one actually is a yes, and this actually is a good mistake to make now, because if you make that mistake again later, it's going to also change your answer to a future problem. So the answer actually is yes, we can do a rotation, 90 degrees clockwise. I'm going to say around L. And then we would translate, is it 7 units? Yeah, so look, here it is rotated around L. And I go 1, 2, 3, 4, 5, 6, 7 units to the right. Okay, and 1, is it congruent? Okay, this is an obvious no, right? However, I'm going to play devil's advocate again. Do you see this is a side length of 1? Oops, hold on, let me move that one out of place. Do you see this is a side length of 1? And side length of 1, right? 1 and 1. 2. Oh, that's a 3. I grabbed the 3. 3. 3. Huh. So how are you saying they're not congruent when all of them have the same side lengths? What do you think, Landis? Inside of it. Yes, so what we're tying into what we did yesterday. What is the area of A? Yeah, same perimeter, different areas. Great tying into yesterday's lesson. What's the area here? 1, 2, 3, 4, 5, 6, 7, 8. And what's the area here? 1, 2, 3, 4, 5. So, no. I do think it's important to point out things that are the same, because I don't want us to be confused by them later. So we would say, no, we do have the same perimeter, but different area. And obviously they look different, right? So it's an obvious no, but I still want to make sure that we're noticing some of those things. 2, are they congruent? Who says yes, raise your hand. Who says no, raise your hand. Okay, again, it's an, oh, is that a no? Just a delayed yes? Okay, yes, they're congruent. What's the rigid transformation then? Or what's the sequence of rigid transformations? Yeah, that's number 3. Thank you for correcting that. Garrett? Good. Reflection over y-axis. Then we translate 1 right, 1 down. All right, and now we have saved enough time to go over these ones, because these ones are some really good discussion ones. Number 4, are they congruent? Who says yes, raise your hand. Who says no, raise your hand. Again, it's a unanimous no. Please explain why. Who's a volunteer to talk about why? Callista. Good. The angles are not the same. So this is one where we do want to make sure we're being precise if we're using our tracing paper. And I want to point out that the side length's the same. Try that again. Do you see how I just rotated it, and do you see how it lines up perfectly there? So are the side lengths the same? Yes, but what is it that's different? Angles, yeah. So no, although side lengths are the same, I still like pointing out what is the same. The angles are different. And if the angles are changing, then it's not a rigid transformation. And here's my favorite one. Number 5. Are they the same? Raise your hand if you say yes. Raise your hand if you say no. Unanimously incorrect. This is about precision, folks. Precision. Watch this. Is close enough the same as exact? Do you see it? Okay. Watch. I know that was hard to tell, but that was kind of what I was alluding to with Nadia's earlier one. We have to be really precise, first of all. Second of all, look. What's the area? 9. What's the area here? 1, 2, 3, 4, 5, 6, 7, 8. So are they close in size? Yes, but are they exactly the same? No. Nope, there is no close enough. Only in handshoes, what is it? Horseshoes and hand grenades, as the saying goes. No, areas are different. Are they just barely different? Yes, but are they different? Yes. Okay, voice is off. It's time to finish up, guys. Please turn to your summary. See this one right here? This one's a good challenge. In-person students, if you do this and show me the answer tomorrow, I will give you a candy. But it's not very closely related to this lesson, which is why I'm not going to take time on it. If you want to do that and show me tomorrow, then it'll be a candy. But we're moving on to the summary. Let's highlight. Okay, how do we know if two figures are congruent? You guys use your tracing paper a lot, and if we can trace it on the tracing paper and then just move the tracing paper so that it copies onto the other figure, then that means they're congruent. Thank you for highlighting with me. So pay attention when you're moving your tracing paper, pay attention to how you're moving that tracing paper, because that can describe a sequence of translations, rotations, and reflections. If you're twisting your tracing paper, that's a rotation. If you're flipping your tracing paper, that's a reflection. If you're just sliding it, that's a translation. And if you're doing a combination of those, that would be that sequence of transformations. And we also saw this. How do we know when two figures are not congruent? Well, sometimes it's pretty obvious, and we can just tell that obviously they're not congruent. But I also want you to be careful about some interesting features. So we're actually going to skip down for the sake of time. We're going to skip down here where we see these polygons. Do you notice how this rectangle has side lengths 3, 5, 3, and 5? And do you see how this quadrilateral has 3, 5, 3, 5? But do you see how they're in a different order? And that's what it's talking about here. 3, 5, 3, 5 for the rectangle, and 3, 3, 5, 5 for EFGH. So does the order matter? Yeah, so we want to make sure we're careful about that. And yeah, that's all for that. I'm not going to highlight anything else. I kind of liked that concept there, but now it's skip to that cool down. Last problem of the day. Please describe a sequence of reflections, rotations, and translations that shows how quadrilateral ABCD is congruent to EFGH. There are multiple ways to do this. Yeah, it is pretty big, but I bet you can still figure it out. I would like to translate it into this position. And when I translate it into that position, what's the next move? Can you see it? It's not rotation. Reflect. Yep. I'm going to write that down. That's not the only one. There's lots of others. Opposite or backwards copy, right? That's our mirror image. So we translated it right. How many units? 1, 2, 3, 4, 5 units. And then we would reflect over line, what is that, HG. And of course, this is not real software. So when I reflect, it would land up right here, but my software doesn't allow that. Ladies and gentlemen, we finished our lesson. Your homework is the Lesson 12 practice problems. Please make sure you're working on that tonight. That's it for today. Have a good one. We'll see you next time.